Welcome to Module 11, Fossil Primates. This is where we start talking about fossils, and fossils will take up much of the discussion of the rest of the course. So when we talk about fossils and the fossil record, it's important to understand the way we interpret the material that we discover. The most important is probably the dating, and there are multiple ways that things can be dated in the fossil record. I want to discuss those just a little bit. One of the most well-known dating methods is carbon-14 dating. When an organism dies, the carbon-14 in its body starts to decay to another isotope of carbon, carbon-12. The half-life of this decay is 5,730 years. So that means that every 5,730 years, half of the carbon-14 decays to carbon-12. When the ratio of carbon-14 to carbon-12 is measured, it indicates the age of the fossil. The difficulty with this method is that by about 60,000 years ago, there is so little carbon-14 left that it cannot be measured. So that puts an upper limit on the dating using carbon-14 to around 60,000 years. One of the most useful dating methods for human paleontology is potassium-argon dating. East Africa is very volcanic, and when volcanoes in this area erupt, they send out an ash plume. In that ash, which settles on the Earth, there are potassium crystals. The potassium decays over time into argon, and so the ratio of potassium-argon indicates how long ago that volcano erupted and that layer of Earth was laid down. The half-life of the potassium-argon method is 1.26 billion years, which means that very old events can be dated. Notably, it also produces very precise dates, within 10,000 years optimally. The use of this method requires the principle of superposition. Different layers of Earth can be dated. The overall principle is that the older layers are below the younger layers. So when you date two layers, if a fossil is found between those two layers, those serve as brackets. The upper is the younger date and the older is the oldest possible date. This is known as relative dating. As you probably know, the Earth has a magnetic field. When you hold a compass, it points north. This magnetic field reverses at irregular intervals throughout the Earth's history. This leaves indicators in the soil. By looking at the polarity of the iron in the Earth, one can determine the age of that stratigraphic section. The last method I'm going to mention is biostratigraphy. Certain animals only appear at certain times in the fossil record. So if a fossil is found in an area that is datable and then found elsewhere in an area where perhaps there is not potassium-argon dating available, that fossil can serve as a marker for the age of that stratigraphic layer. Probably the most well-known of this is the disappearance of the dinosaurs. If a dinosaur is found, you know that that layer must be older than 65 million years. Ideally, when discovering fossils, you have a good control of the stratigraphy, in other words, the layers of the soil, because it can tell you the environment in which the fossil was laying down. Here we see an ancient river channel. Knowledge of distribution of water is critical because primates require drinking water every day. In locations where there is water, you have a higher likelihood of finding a primate or human fossil. Occasionally, you find remains of plants. This is known as paleobotany. Coprolites are fossilized fecal matter. In this photograph is an ancient hyena coprolite. Taphonomy is the study of the depositional environment and the events that occurred between the time the animal died and it was discovered. Typically, when an animal dies, it is eaten, scavenged by animals, it can be trampled, and then is subject to rain and then deposited in the fossil record. All of this can tell us the environment in which the fossil was laying down. It's important to keep in mind that fossilization is a very rare event. It is fairly unusual that we have enough samples of a species to get good biological parameters, although there are some exceptions in the fossil record of humans. So when we try to interpret the relationships among taxa, we have to keep in mind that whatever we're seeing is an oversimplification of what was a much more complex evolutionary history throughout time. When we look at anatomical characters in the fossil record, there are two different types of information, broadly speaking, that we're looking for. Adaptive information is the information about what the animal did, what it ate, how it moved, so forth. The other type of information is information that tells us about evolutionary relationships. The difficulty is that we must be careful when using adaptive information to infer phylogenetic relationships, because convergent evolution may lead us astray if two relatively unrelated animals have converged on a single adaptation. Most primate evolution happened long after the continents assumed the positions they are in today. This means when we talk about the distribution of primates across the globe, we have to be able to explain how they got there. The evolutionary history of primates, and all organisms, is dependent upon the climate. It is possible to reconstruct temperatures in the past by taking deep sea cores. Oxygen is composed of two isotopes. An oxygen-16 lighter isotope more easily evaporates into snow and rain and gets trapped in glaciers and poles during cold eras. So in sections of deep sea cores that have high oxygen-18 to oxygen-16 ratios, we can infer that these were relatively cold periods of time. Overall, over the last 65 million years, since the extinction of the dinosaurs, there is a trend towards cooler and drier climates. The evolution of the primates coincides with the disappearance of the dinosaurs. When the dinosaurs disappeared, multiple ecological niches appeared into which animals like primates could evolve. The last 55 million years is known as the Cenozoic era and is typically broken up into three time periods: the Eocene, the Oligocene, and the Miocene. Primates would have evolved sometime during the early Eocene, around 55 million years ago. There are multiple hypotheses for the origin of primates. The Eocene coincides with the spread of angiosperms, the flowering plants. Such plants attract insect pollinators, which would have been natural prey for early primates. It's noteworthy that primates have forward-facing eyes, much like visual predators. The earliest candidate for the ancestry of primates are the Plesiadapiforms, who lived between 50 and 65 million years ago in North America and Europe. They are not primates themselves. They possess claws rather than nails, for example. However, they are a good generalized mammal from which it would not have been difficult to evolve primates. The earliest primates we know of exist between 35 and 58 million years ago, the Adapids and the Omomyids. These are ancestral strepsirrhines. The Omomyids were small galago-like creatures, insectivores, leapers, much the way galagos are today. The other earliest primates are the Adapids. These appear to be ancestral to modern lemurs. They are large, monkey-sized, diurnal, arboreal quadrupeds, much like lemurs today. Ida, a 47-million-year-old fossil preserved with soft tissue and even stomach contents, is probably the most well-known adapid. In terms of the anthropoids, the best evidence comes from the Oligocene, 25 to 45 million years ago. The best evidence has been discovered in the Fayum, Egypt, which 40 million years ago was a tropical rainforest, but today is a desert. The two species discovered there are Opidium and Egyptopithecus. Opidium is a monkey-sized primate with 3 premolars. and Egyptopithecus is a monkey-sized primate with 2 premolars. This means that these two species are actually at the split between New World monkeys and Old World monkeys. When we look at New World monkeys, the biggest question is how primates traveled across the Atlantic Ocean to South America. We know we have primates by at least 27 million years ago. The best hypothesis is that they traveled on giant floating mats of vegetation. There are relatively few fossils preserved in the rainforests of South America. The most well-known is probably Branicella, which is notable for its sharp leaf-cutting teeth and its relatively large canines. In terms of the ancestry of apes and humans, we do have a reasonably good fossil record for many fossil apes. The Miocene, between 23 and 7 million years ago, is often called the Age of Apes. This is when there was an expansion of rainforest across North Africa and even into southern Europe. There are relatively few monkey species that we find, but many ape species, many more than we find today. Probably the most well-known ape from Europe is Dryopithecus, also known as the oak ape. I'll draw your attention to the image on the right. You can see in the picture the long forearm and the long fingers. This indicates that it was a suspensory ape, which is the adaptation shared by African apes today. The most well-known fossil ape in Asia is Shiva-Pithecus. This fossil is remarkably similar to orangutans today and is considered an ancestor to orangutans. However, the postcranial skeleton of Shiva-Pithecus is very much like a baboon, so we interpret this to have been a terrestrial version of an orangutan. The best candidate for the African apes is Proconsul, which would have had multiple species in the genus. This was a medium-bodied primate, roughly the size of a baboon up to a chimpanzee, an arboreal quadruped, and critically lacked a tail. The last fossil ape I'm going to speak about is Gigantopithecus, which was a large Asian ape that shared the bamboo dietary adaptation of modern-day pandas. This would have been an enormous ape, roughly 3 times as large as a modern gorilla. Here on the right we see a reconstruction of what that ape would have looked like. As the Miocene ended, the climate changed, and the Earth became much drier and cooler. This meant that tropical rainforests in Europe and North Africa receded to the distribution of rainforests we see today. This led to the extinction of many species of ape and the rise of monkeys, who were more able to adapt to drier, more varied environments. We have a very poor fossil record for African apes in general. There are 1 or 2 teeth that have been proposed as candidates for the evolution of chimpanzees. In general, our understanding of the evolution of African apes is based on the DNA. However, our confidence in the DNA is fairly strong since the DNA divergence times are consistent with what we know from the human fossil record.